Hello, and welcome to another lesson from Level Up Mathematics. In today's lesson, we will be representing ratios as tables, graphs, and proportions. Now, you're already pretty familiar with using tables to represent ratios, but today we'll be adding on graphs and proportions. So in example 1, it says, at a birthday party, the ratio of cupcakes to kids is 3 to 2. So in other words, there are 3 cupcakes for every 2 kids. And in part A, they want you to complete the table below to show the different possibilities for the number of cupcakes and the number of kids. Now, be careful when you put this original ratio into the table because the 3 represented the number of cupcakes. So I want to be sure to put a 3 here. The 2, for every 2 kids, there were 3 cupcakes. All right. Now, from previous lessons, you've learned that you can scale this table up using multiplication. So 2 times 2 is 4. 3 times 2 is 6. We could scale by 3. 2 times 3 is 6. 3 times 3 is 9. 2 times 4 is 8. 3 times 4 is 12. 2 times 5 is 10. 3 times 5 is 15. 2 times 6 is 12. And 3 times 6 is 18. So those are some different possibilities for the number of kids and the number of cupcakes. Now in part B, it says use your table from part A to make a plot of the points on the grid where the number of kids is the x coordinate and the number of cupcakes is the y coordinate. All right, so I'm going to start with my first entry in the table, 0, 0, and we'll plot that right here at the origin. So on our graph here, number of kids is plotted on the x-axis, and number of cupcakes is plotted on the y-axis. Now, our graph is going 5, 10, 15, 20, but I want you to notice that the smaller tick marks would be scaled by 1. So 1, 2, 3, 4, and so on. So even though the graph is scaled by ones, they did not write out every single number. All right. So if I wanted to plot the next ratio, 2 to 3, there are 2 kids, 3 cupcakes. So on my graph, I'm going to go from 0, 0, I'll go right 2, and then up to 3 cupcakes. 1, 2, 3. So 2 kids, 3 cupcakes would land right there. All right. Now we want to plot 4 kids, 6 cupcakes. So 4, 1, 2, 3, 4, 5, 6. Okay. Hopefully you're going to see something interesting happening here on this plot when we plot these ratios. All right, now we're going to plot 6 kids, 9 cupcakes. So 6 to 9 would be right there. Then 8 kids, 12 cupcakes. 10, 11, 12. Notice what's happening with the points here. 10, 15. And 12, 18. All right. Now, notice that each one of these ratios, when we graphed them all together on a coordinate plane, they formed a straight line. Okay, we'll be talking about that more later. All right, part C. At a larger party, there are 30 kids. If the ratio of cupcakes to kids stays the same, how many cupcakes will be needed? Now, this would be hard to answer from the graph because our graph only goes up to 20 kids. So if you can't get the information from the graph, you would need to go back to the table. Now, we're trying to find out the number of cupcakes for 30 kids. So I'm going to put the 30 on the top row because that's where the number of kids were. And I'm going to pick one of these ratios, 2 to 3, 4 to 6, 6 to 8 to 12, 10 to 15, one of them that's easy to scale to 3. Okay? Now, I'm going to choose the 10 because for me, to get from 10 to 30, it's easy for me to see that I'd have to multiply by 3. So if I multiply the 10 by 3, I'll have to do the same thing to the 15. And that would get me to 45. So there would have to be 45 cupcakes needed. Now, real quick before we move on, I want to show you that I did not have to choose the ratio that I did. I could choose a different ratio and get the same exact answer. So let me just choose one other ratio to prove that to you. What if I would have chosen, say, the 6? What would I have to multiply 6 by to get to 30? Well, hopefully you said times 5. So if I multiply the 6 by 5, I would have to also multiply the 9 by 5. And 9 times 5 is 45. So I still get the same answer no matter which ratio I pick to scale up. So choose the one that makes the best sense to you. All right. Let's see. Example 2. In a 6th grade class, 3 out of every 5 students have brown hair. So in part A, they want us to represent this ratio with a table. So for every 3 students with brown hair, sorry, for every 5 students, 3 have brown hair. So our first ratio would be 3 to 5. Now, just like in the table above, I can scale this up. I can multiply by 2, and that would give me 6 to 10. I could multiply by 3 and get 9 to 15, or I could multiply by 4 and get 12 to 20. All right, part B. Form fractions from this table using the first row as the numerator and the second row as the denominator. All right, so my first fraction would be 3/5. My second fraction would be 6/10, 9/15, and 12/20. All right, problem C. What does each of those fractions from part B reduce to? Think about it. All right, hopefully you said they all reduce to 3/5. 3/5 is our original ratio, or our most simple form ratio. Now, in part D, we're going to use that 3/5 to answer this next question. D, if there were 40 students in the class, how many would have brown hair based on this ratio? Fill in the missing numerator below. Now, just like up here in this table, we scaled our ratio to find the answer to question C. I'm going to scale my ratio here. So my original ratio is 3 to 5. I want to scale this 5 to 40. So ask yourself, what would I have to multiply? In other words, what is 40 divided by 5? Well, hopefully you said 8. So if I scale the denominator by 8, I must also scale the numerator by 8. So 3 times 8 is 24. So in this particular class, if there were 40 students, 24 of them would have brown hair. Now, the equation from part D that we just worked with, this 3 over 5 equals 24 over 40, this is a very special equation that you're going to see all throughout the rest of your math classes. This equation is called a proportion. Proportions are equations stating that 2 ratios are equal to each other. We can solve proportions by scaling both the numerator and denominator by the same number. So in problem D, we scaled both the numerator and the denominator by 8 to answer the question. So proportions allow us to solve ratio problems without using a table. All right. Example 3. The ratio of girls to boys at Johnson Middle School is 4 to 3. This relationship is shown in the graph below. Use the graph to complete the table. So what I want you to notice is this table has 1, 2, 3, 4, 5 points. And what they want you to do is find the coordinates of each of those points and put it in the table. So we know this first one down here is 0, 0, and in fact that part of the table is already filled out for you. So let's get our next point. 1, 2, 3, 4. 1, 2, 3. So 4 girls, 3 boys. 4 to 3. All right. So our next point. Let's see. 5, 6, 7, 8 over 8. 1, 2, 3, 4, 5, 6. 8 to 6. So 8 girls, 6 boys. Our next point right here would be 10, 11, 12. I'm going over 12, up 9. And then our last point, let's see, that's over 16. And this is 10, 11, 12, and up 12. So 16 girls, 12 boys. All right. Represent the ratio of girls to boys as a fraction in simplest form. So that ratio would be 4 to 3. That was our simplest form ratio. All right, part B. If there are 120 boys at Johnson Middle School, set up and solve a proportion to determine how many girls there are. All right, so remember, a proportion are two ratios that are equal to each other. So I'm going to say there are 4 girls for every 3 boys. Okay, and I want to know how many girls are there for 120 boys. All right, so here's our proportion. Remember, a portion is two ratios that are set equal to each other. And the way we solve a proportion is we scale up. So I'm trying to get from 3 to 120. So what you want to do is see how many times will 3 go into 120. So 3 goes into 12 4 times. 3 goes into 0 0 times. So that means we're scaling this proportion by 40. So if I scaled the bottom by 40, I must scale the top by 40. So 4 times 40 would be 160 girls. All right, problem C. If there are 200 girls at Johnson Middle School, how many boys are there? If there are 200 girls, then how many boys are there? Set up and solve a proportion. So again, I'm going to start with my basic ratio, which was 4 girls to 3 boys. So what I want you to notice that in my proportion, I'm putting the girls on top, the boys on the bottom. Now, that's important because in part C, they've given you the number of girls. In part B, we didn't know how many girls there were. But in part C, they've told us how many girls there are. There are 200 girls, and they want to know how many boys. So this time, we have to scale the numerator. We have to determine what are we scaling the numerator by. So I want to know how many times will 4 go into 200. So 4 goes into 20 5 times, and 4 goes into 0 0 times. So 4 will go into 250 times. So I'm going to multiply the top by 50, and I'm going to scale the bottom by 50. So 3 times 50 would give us 150 boys. All right, example 4. Brianna charges an hourly rate for repairing computers. The graph shows the shows the amounts Brianna charged for different numbers of hours she worked. Based on the data in the graph, set up and solve a proportion to determine how much Brianna would charge for a computer repair that takes 9 hours. Okay? So first of all, I want you to notice in this graph, they've given us the ordered pairs on the graph. The X value, let me highlight this. The X values are your number of hours, and the Y values are the amount that she charged. So I can choose any of these ratios I want, but I want to use one that would easily scale the hours to 9. So I wouldn't choose the first point, the 2 comma 45, because 2 does not go into 9 evenly. Okay, now let's look at our next ratio. 3 hours, 67.50. 3 will scale to 9 much easier. So I'm going to say 3 hours to $67.50 is our first ratio. And we want to know how much would she earn, so I don't know the earnings, for 9 hours. Notice how in our ratios, I'm keeping the hours on the top in both ratios. So I think this one's pretty easy to scale. 3 goes into 9 3 times. So I'm scaling the top by 3. So I must scale the bottom by 3. So I'm going to take 67.5. I guess I could do 50 and multiply it by 3. So 0 times 3 is 0, 3 times 5 is 15, carry the 1, 3 times 7 is 21, 22, carry the 2, 3 times 6 is 18, 19, 20. Then there were 2 numbers after my decimal, so I must move my decimal in 2 places. Done, done. So Brianna would earn $202.50 for working 9 hours. Now, I want to show you something else. I could have set up my original ratio a little bit differently. I could have put the amount she earned, $67.50, on the top, and I could have put the hours on the bottom. Now, if you set your ratio up this way, perfectly fine. But just remember, when you're solving it, the 9 hours now must go on the bottom. All right, so just be sure that if you've got hours on the bottom, that in your second ratio, the hours better be on the bottom again. I would still scale by 3. I would still scale the top by 3. Either way, it's going to work out to $202.50. All right, and that concludes today's lesson, Represented Ratios with Tables, Graphs, and Proportions.